All right, so we're going to look at one final example here. I'd like you to take a look at this here. We have some information about this, so we're going to go ahead and measure this out here. We have the measure of angle R is 130. I'm going to mark that in here. Measure of angle P is 75, and I want to calculate this angle here, given that this is a right angle. Okay, so some of you know, wait a minute, this is a quadrilateral. That's easy. So that means the interior angle sum to 360, so it's going to be 360 minus the sum of the others, 75 and 130 and 90, right? So it's 360 minus, in this case, 205, 295 here. And that means the last angle, I think, is 65 degrees, right? Easy peasy, lemon squeezy. But of course, that is all dependent on one very important thing here. How did you know that the interior angle sum to 360? Well, one thing to note is that, wait a minute, we can do this for a quadrilateral here. I can kind of take this quadrilateral and split it like this here. I can draw a diagonal like this and split it into two triangles here. Each of these triangles, we know we've proven that the interior angles of the triangle sum to 180, so therefore we can put these together and get 360 out of this. Okay? And some of you may know, wait a minute, there's a formula, there's a theorem here, that if you have a polygon with n sides, right, if you have an n-gon here, the sum of the interior angles is going to be, in this case, 180 times n minus 2. Some of you may have known this theorem already. Now, of course, why is it true? Is this a theorem, so we should be able to prove it here. So I'm going to do a very brief proof of this. It's not going to be a full formal proof of this here because it requires some techniques that we may not necessarily know yet. I'm going to show you sort of a intuitive method for showing this here. So let's say I have myself some polygon here. 1, 2, 3, 4, 5, 6. I think I have a 7-gon here, right? So here I'm going to let n equal 7 here for this example. Okay. Now, obviously, this will work for any polygon. So I'm going to pick a point here. Now, we can divide this into triangles. So notice how before we took our quadrilateral, we divided into triangles by going along a diagonal here. And I'm going to do the same thing. But this time, in order to sort of try to avoid haphazardly putting in diagonals here, I'm going to put in diagonals in a very specific way. I'm going to start at A, and I'm going to draw every possible diagonal I can. Now, clearly I cannot connect A to itself, and I cannot connect A to either of its neighbors because it's already been taken. So let me connect it to the other vertices here. So I can do this, this here, and this here. Okay? So we can kind of do something that looks like this here. And we see that from this point, we can radiate ourselves some number of polygons here. So notice how in this situation here, from this, we were able to draw, well, in this case here, from this vertex, we draw n minus 3 diagonals here, right? We're drawing n minus 3 diagonals because you can't connect, so for an n-sided polygon, an n-gon, you have n vertices. To create a diagonal, you have to connect two vertices together. You can't connect a vertex to itself or either of its two neighbors. So that's n minus 3 here. Now, why is it n minus 2? Well, that's because we're actually dividing a zone into some number of subzones by using these diagonals here. And I think intuitively it makes sense that if you have a specific zone and you're dividing into subzones using non-intersecting partitions, walls, then the number of zones you're going to have is going to be one more than the number of partitions, right? So if you have a zone like this here where there's no partitions, there's going to be one zone here. If you have one partition, you're going to create two zones, 1, 2. If you have two partitions, you're going to create 3 zones, 1, 2, 3. 3 partitions gets you 4 zones, 1, 2, 3, 4, right? And so on and so forth here. So in this situation here, because we have n minus 3 diagonals, and notice that diagonals there, these diagonals come from the same point, so they're never going to intersect. So that means we're guaranteed that these partitions are going to remain separate. So there's going to be n minus 3 of those, so we're going to divide this into n minus 2 zones, and that's where the n minus 2 comes from here. Now, again, like I said, granted, this is not a perfect proof of this particular theorem here. If you want a full proof, one of the ways to do a full proof is to use something called induction, and that's something that you can try to look up on your own. There are some proofs out there that you can show that the interior angles have to sum to 180 times n minus 2 using this idea of start with a triangle and then build up every polygon from this triangle here. But that's something for another day.